Today's question is from HackerRank. The topic is about diameter minimization. The question given a graph, the number of vertices n, and and this problem assumes that for every vertex in this graph, it has an out degree equals to m. So n, the number of vertices, and m, the number of off degree for each vertex. This problem asks us to find out the graph, the strongly connected graph with minimum diameter. The scoring scheme allows some mismatch between the optimum diameter and our answer. Let's review how we can approach to this question. We reiterate the question. Given two integers n and m, n is the number of vertices and m is the out degree of each vertex. We want to create a graph that having the diameter d as small as possible. The diameter is defined to be the greatest distance between any pair of vertices in the graph. For this question, the out degree for each vertex is m. We claim that the diameter d of this kind of graph should satisfy the following inequality: 1 at m all the way until m to the powers of d must be no smaller than the number of vertices, which is n. Let's prove it. So given any vertex in V, the number of vertices that can be reached in exactly 0 step is at most n to the power of 0, which is 1. Similarly, we want to find out how many vertices can we reach with only exactly 1 step from V. Then it is at most m to the powers of 1, which is 2. Here, we assume that n equals to 2 for discussion. We say at most because if this is a loop, then the vertex may be V itself. Similarly, by induction, we can see that the number of vertices that can be reached in exactly 2 steps from V is m to the power of 2. With this pattern, we concluded that given a vertex V, the number of vertices that can be reached in exactly k steps from V is at most m to the power of k. Then the number of vertices that can be reached within k steps will be the sum from 1 to the m to the powers of k. Then the vertices that can be reached within d step, here d is the diameter of the graph, will be this formula, this summation. But given the definition of vertex of diameter, it is the greatest distance between any pair of vertices. So it means that by this induction, we know that all the vertices must be reachable from any vertex within these steps. So we reach our conclusion. The left-hand side, which is the number of vertices that can be reached within these steps, must be larger than the number of vertices in the graph. So our construction, our approach of the graph is that for each vertex I, we add edges from vertex I to vertex m times I plus alpha, and after that we take modulo over n. N is the number of vertices in the graph. Alpha lies between 0 and m, or you can set it to 1 to m plus 1, that's okay, which is an integer. Let's take a simple example. Let m, the algebraic for each vertex to be 2, the number of vertex to be 5. Then for vertex 3, we add edges from vertex 3 to vertex 2, which is m, times 3, which is the vertex index, plus alpha. After that, we take modulo over 5. Then alpha lies in between. Alpha 1 can be 0, 1. Let's see. 0, 1. Is that correct? 0, 1 here should be m minus 1. Is that okay? Right. To m minus 1, which is 1. Okay. So two vertices can be reached with one step, and the formula is here. By induction, we can derive the next layer, and we gradually find out the pattern here, and we concluded that the vertexes for vertex I, the vertices that can be reached in exactly as steps from the vertex V are this formula here. Then we rearrange, when we change the variable alpha to beta to align the subscript with the power of m. So we finally arrive at this formula. The formula is the number of vertices that can be reached from I exactly as steps. Okay, so we focus on the second part, which is not related to the vertex I. The second part is essentially the representation of any number that is smaller than n to the power of s in base m. If you replace it by 10, then it will be more clear. Sorry. If it is 10, it's just our usual representation of number, which is smaller than 10 to the power of s. S can be like 3. So the right hand side is the representation smaller than 1000 in this example. It's quite straightforward. Okay, so we further simplify. Knowing the representation, we can further simplify this, that this equation is equals to this one, and we replace the right hand side of this by a single beta, and beta is between 0 and n to the power of s, and smaller than n to the power of s, and which is an integer. Okay, So this is the second conclusion we arrived. We with retrospect to the first conclusion, that we know that given a graph, we know by the definition of diameter, we have this inequality, and we use the formula of a geometry series, and we know that by some simplification, n must be no larger than m to the powers of d plus 1. Okay, so under our approach, we know that if the number of vertices smaller than m to the powers of k, then we can starting from any vertex, reach any vertex in the graph with k steps. This is the second conclusion we made here, because beta covers all the because beta covers the range of beta will be reside in well resides in this range. So if since beta resides in this range, okay, and the vertex can be reached, vertex vertices vertices reach reachable vertices is this one. So by taking module and the range of beta, we can, if if this one, replacing this one. If m to the powers of k is larger than n, then beta can cover all vertices. The number of vertices is n, then it can cover all vertices. And also by the first conclusion, by the definition of diameter, we know that number of the number of vertices must be smaller than m to the powers of diameters plus 1. So using our approach, we can only guarantee to reach any vertex in V, which is this formula, with at most d optimum, we choosing the smallest d plus 1. So our approach builds a graph with a diameter that differs from optimal by at most 1. Okay, so let's implement this approach in simple Python. Just copy. Where is it? Our approach. Okay. For each vertex, add edges from vertex I to vertex m plus times I plus alpha. Alpha relies in this range. The output of this question is the vertexes. The, the first line is the diameter of the graph we generated. The second line is the vertexes that can be reached from vertex 0. The third line is the vertexes that can be reached with, uh, uh, except for the top number. Each line represents a neighbor for each vertex from 0 to n minus 1. So we can just print out our neighbors. Our neighbor is mode n for alpha in range. In range n. Okay, and the join with use map str. Okay, join map str. This, let's see, m plus times vertex plus alpha for alpha in list m minus. Okay, starting from the second line, print out the neighbors for each vertex. For the first line, we need to print out the diameter. How to find out, given graph, how to find out diameter? We can use the breadth first search to find the diameter. Okay. First define diameter d equals to 0, let's see, zero, okay, minus 1, that's okay. Return d, and starting the diameter, we need to disclaim some variables for BFS. First is a distance for each vertex, which is let's let's define distance vertex v to distance I dist I is the distance from the vertex v to vertex I. Okay, the number of vertexes, and we need a q. We can use the dq in Python. And we also need a visited the set contains all the visited record visited vertexes q bfsq. At first we will have just insert a 0 into it, then we start our BFS while q. Okay, so first we want to pop a vertex, the current vertex, equals to q pop left, q pop left, pop left. Okay, q pop left, and we mark it as visited. Current is not necessary, just use vertex. Oh, sorry. Vertex. Okay. Append it, and for each neighbor, for IGHBR, in a neighbor is this equation, right? The neighbor and vertex times alpha vertex plus alpha modulo n for alpha in list range. Okay, we do what? Then we if the neighbor has not been visited, then we first push the neighbor into the queue. Then it was update the neighbor's distance to be the, let's say, to be itself or vertex neighbor. So one step, suppose the distance from Okay, let's see. dq minus 1. Distance vertex plus 1. We take the minimum of it if neighbor is not in TQ. Okay. Let's see. Okay. For each neighbor, we do this until we visited O vertex. Some for each vertex, right? So let's see. We something is lacking here. Let's see. Okay. This one's okay. For each vertex, do a BFS to find out the maximum distance from V for V in range n. Distance initially equals O to infinity, except for V itself. The distance to itself is 0, and no one has been visited. We do the BFS starting from inserting any vertex into the queue, and let's say visited a pained vertex. Okay, a pained vertex. Or you can just a paint V. Alright. Then after running one BFS for each V. Okay. Then we will take the maximum of D with the maximum of distance, right? Error. Non-ASCII characters. Where is non-ASCII character? You mean alpha? Wow. ちょっと待ってください。大変だな。どこ？This one? Okay. Expected. Alright, alright. For join. Okay, okay. Which line? Line 28, 28. For, okay. Was never closed. Join. Print. Sorry. Print. Join. Okay. Map. Alright, alright. String to this list. Alright. Is it right? It's alright. Is it? Dun. TQ is not defined. What do we need to import? From collection, import DQ. Runtime error. Set has no attribute append. Alright, alright. My fault. Set. Where is the set? Set is here. Visited. Add. Okay. We passed the sample test. We try to submit it. Okay, that's it.